Everyone, we talked about half-life, so now we can use that idea to determine a rock's absolute date, or its radiometric date. So what are we talking about here?
We are talking about using how quickly a rock decays, if it's radioactive, to determine just how old that rock is.
So you've got the parent isotopes, that's the original element, like the carbon-14 or the uranium-238.
Yeah, and it changes into something else. It changes into lead in that particular case, and that's the daughter isotope that it's trying to become.
And we've talked about the half-life being the time it takes the original sample to decay to half of its original amount. And then for that amount to decay again one more time. So we've seen this graph many times, whether we're doing the dice and pennies in class or we did the radiometric dating game on the simulator. We see this curve, and at every half-life you have half of the original amount. So in this case, we started with 10,000 grams. At one half-life, looks like 24 days, we're at 5,000 grams. 24 days later, we're at 2,500 grams, and you just keep going, having the amount that remains. So in terms of what we do to actually radiometrically date things, we use this little device here. What in the world do they have on the simulator?
So what we see here is a Geiger counter, and basically what it's doing is reading the amount of radiation that's coming off of whatever object it's trying to test. And in this case, a tree that appears to be dying. And the moment the tree dies, it begins to let off less radiation than it did when it was alive, because it has less of that radioactive material left in it.
So as time goes on, you can see that the amount of carbon that was there in the beginning has started to decay. We've now just hit one half-life, so around that 5,000, 6,000 years, we're at about 50% of the carbon that we had in the beginning. When we get to a second half-life, we'll be at 25% of the carbon remaining, and so on and so forth. So based on the percentage, like right now, if I wanted to track 35% of the carbon, I'd know that I'm already around 10,000 some years old.
Now here we are at two half-lives, and you can see we're right at about 20.
Let's try this for a rock then. If I have the rocks come out of a volcano, those rocks cool. Once they cool, we can then watch the years go by, and you can see the years are flying by here, and we're not reading anything. Why?
That's because this isn't a living thing. Only living things have carbon-14 to measure, and we need to come up with another substance that we can measure the radioactivity of.
So in a rock, there's no carbon, so we look at the uranium that's radioactive. And if we reset this with the uranium decay, we start off with 100% of the uranium, and you can see as the years go on here, the uranium is decaying. However, the half-life of uranium, remember, is 4.5 billion years, so it's going to take a lot longer for us to get to 50% of our original material.
Right, we're already at 2 billion years, and as we approach one half-life, we should eventually hit about 50% of the uranium.
So the rock would be half uranium and half lead.
Yes.
So if we come across a sample that is 25% uranium and 75% lead, we know it's been around for
two half-lives,
which in this case is around 9 billion years. And on our planet, we have never seen a rock that has that ratio of uranium to lead, because the planet has only been around for about 4.5
billion years. So what we see in uranium is 50%.
50% uranium, 50% lead. And if they want to use uranium for reactors, they've got to separate the radioactive uranium from the lead. So what we did in the simulator was we used the Geiger counter and walked around and looked at different materials here, like this animal skull. We can see that there's 98% of the carbon-14 left. So moving the slider bar here to that exact percentage of carbon remaining, you can see that 98.2% of carbon gives you 152 years old for the animal skull.
And a very happy, ringy-dingy little smiley face.
If I moved it over to the tree is at 100% carbon.
It's because it's still alive.
So it still might be old. I mean, it's been living, but radiometric dating only gets things when material starts to decay.
Because when a living thing dies, it doesn't replace the carbon-14 any longer.
And again, coming down here to the fossils, the further down into the rock layers we get possibly older things, and this has no carbon whatsoever.
So we got to switch over to uranium and
There's
check that out.
Still no uranium.
Ooh. Well, then you need something else.
So this was a living thing. We need another radioactive element. And if we click on another radioactive element that has a half-life of maybe 1 million years, not that element, 10 million years, there we go.
There we go. And we have a percentage of that. We can do the same process and figure out about how long Mr. Fish has been dead.
So about 14.4% of this custom element left. Looks like we're around 28 million years.
Yep.
When we find things in rock layers, we can guess their ages, which is what we're going to do in the next topic, but we can get their absolute real date if we use this radioactive decay and radiometric dating.
Agreed.
All right, talk next time.